Okay, let's unpack this. Imagine a system, right? It handles nearly 40 billion messages every single day.
It's a staggering number.
Keeps hundreds of millions connected.
Yeah.
And yet, it does it all with this incredibly small engineering team.
That's the kicker. At one point, what was it? Just over 50 engineers for the whole backend?
Yeah, and fewer than a dozen on core infrastructure. It just sounds almost impossible, doesn't it?
It really does.
So our mission in this deep dive, for you listening, is really to shortcut you to understanding how WhatsApp pulls off this, well, this engineering marvel.
Yeah.
It's not just about the raw scale, though. It's about a fascinating, maybe even counterintuitive philosophy behind it all.
That's exactly it. What's truly fascinating here is that their success wasn't really built on, super groundbreaking algorithmic cleverness or throwing huge teams at the problem.
Right.
Instead, it's rooted in something surprisingly basic, almost philosophical, you could say. Simplicity over complexity.
Clarity over abstraction.
Exactly. Clarity over abstraction, and maybe most importantly, resilience over trying to achieve perfection.
Okay, resilience over perfection. What does that mean in practice?
It means they designed for failure. They understood it wasn't just a possibility, it was inevitable.
Yeah.
So they built the system specifically to keep going when things, inevitably went sideways. It's a complete shift from how many systems are conceived, really.
That's a powerful idea.
Yeah.
Designing for failure, not just hoping you can avoid it. So what were the core principles they adopted to make that philosophy real?
Well, their architecture is really rooted in some pretty counterintuitive ideas, like we said. Think clarity over clevernesses.
Okay.
Which basically means preferring small, focused components, each one doing one very specific job rather than some big, overly complex thing.
Simpler is better.
Pretty much. Then there's async by default. Processes hand off work and just move on immediately.
So they don't wait around.
Exactly.
Yeah.
Which is fantastic for absorbing sudden load spikes without, choking the system.
Makes sense.
They also emphasize isolation,
Yeah.
creating these independent islands that can fail alone.
Without taking down the whole ship.
Precisely. And maybe the most impressive bit for a system that literally never sleeps, seamless upgrades.
Without disconnecting users. Wow.
And you mentioned something about the early days.
Oh, yeah. I remember reading something wild, like the founding team actually reviewed every single line of back-end code.
Yeah.
That's an extreme level of attention, isn't it?
Absolutely. And that level of hands-on review, it speaks directly to that clarity over cleverness principle we talked about.
Right.
Because look, at global scale, complexity is just a huge threat to reliability, to speed, everything.
It becomes the enemy.
Totally. So these principles aren't just, nice ideas. They're pragmatic responses to that reality. And absolutely central to making all of this work is a unique programming language called Erlang.
Erlang. Okay. You hear it mentioned with telecom systems a lot, right? So what makes Erlang so uniquely suited to WhatsApp's challenges? Massive scale, constant uptime. What's its core superpower here?
That's a fantastic question, and Erlang truly is the foundational secret sauce here. It was indeed built for telecom, which means it was designed from the ground up for things like lightweight concurrency, fault isolation, and distributed messaging.
So built for reliability from the start.
Exactly. Imagine every single connection, every user session, every little internal task running as its own tiny independent program. Erlang calls them processes.
Okay, like little mini programs.
Yeah, tiny ones. And the Beam virtual machine, that's where Erlang runs, it can spin up hundreds of thousands, sometimes millions of these processes on a single server node without breaking a sweat.
Millions. Wow.
It's incredibly efficient and resilient because of that.
And this leads us straight to that famous let it crash philosophy, which honestly sounds incredibly risky on the surface.
It does.
In most systems, you try to prevent crashes at all costs, right? So how does that seemingly backward idea actually make system more reliable, not less?
That's a great question, and it's really where Erlang shines. The fundamental idea is, well, it's far easier to recover from a small, contained crash than it is to try and prevent every single possible failure.
Because that just leads to complexity.
Exactly, which makes the system more fragile in the end. So because each Erlang process runs in total isolation, its own memory, its own message mailbox, it can crash without taking down the whole system.
Okay. Like that faulty light bulb analogy you mentioned earlier.
Right. If one bulb blows, only that bulb goes out, not the whole street. And then you have these things called supervisors constantly watching.
Oh, watchers.
Yeah, and they restart these child processes instantly if they fail. So failures stay local, they don't cascade.
Okay, so it's not about accepting system-wide failure at all. It's about accepting component failure and having a really robust automatic recovery mechanism built in.
Yes.
And Erlang also has something called a gen factory for managing distributed work. That sounds important for, was it SP scalability? Can you unpack those a bit? What's a gen factory here, and what's SP scalability mean versus, say, just adding more servers?
Absolutely. So think of Erlang's Gen Factory less like a physical factory and more like a standard blueprint or framework.
Okay, a pattern.
Yeah.
Yeah.
A standard way to build robust, concurrent, and distributed components in Erlang. It just simplifies managing and dispatching work across potentially millions of those little processes.
Got it. And SP scalability.
Right. SP scalability, or shared nothing processing scalability. It's fundamentally about maximizing the throughput inside existing servers without necessarily adding more hardware.
So making each server work much harder, more efficiently.
Exactly. You're not just scaling out by adding servers or scaling up with bigger servers. You're making the existing ones far more efficient by making sure processes don't step on each other's toes, they don't contend for shared resources.
Shared nothing.
Shared nothing. Each part is independent, self-contained. For a small team needing to handle absolutely massive load, that's a real game changer.
That kind of efficiency
Is.
Yeah, absolutely critical. Because, I mean, at the end of the day, delivering 40 billion messages every single day means that architecture has to nail three things relentlessly. Raw speed.
Speed, unwavering reliability.
Reliability.
And smart resource isolation, keeping things separate.
Speed, reliability, isolation. Got it. Okay, let's talk about how messages actually move then.
Yeah.
When my phone connects to WhatsApp, it sets up a persistent TCP connection to a front-end server, right?
Correct. A persistent connection.
And you said the connection isn't shared or pooled? It's managed as its own dedicated live Erlang process.
That's right. No connection pooling, no multiplexing, just one process per connection.
It almost sounds wasteful, doesn't it? Like, should you reuse connections?
It might seem that way at first glance, but this design maps so naturally onto Erlang's strengths. It makes managing the life cycle of that connection incredibly straightforward.
How so?
Well, think about it. If something goes wrong with that connection, the process just dies. And all its associated memory and state disappear cleanly with it. Poof.
Ah, so no messy cleanup needed.
Exactly. It's elegant in its simplicity, really. Makes it very easy to reason about what's actually happening. Each connection is its own little isolated world.
What's also interesting, you mentioned this earlier, is that the session process isn't just a dumb pipe, right? It's actively coordinating things.
Yeah, exactly. It talks to backends for stuff like authentication, checking if a user is blocked, pulling any pending messages for you.
And it does this quickly, in parallel.
Quickly and in parallel. That's what they mean by being stateful and smart on the edge.
Okay, smart on the edge. But doesn't pushing so much logic right to the edge, right where the connection lives, doesn't that introduce its own set of complexities, like maybe making upgrades harder or keeping state consistent across everything? What's the trade-off?
That's a really sharp observation, and you're right, it absolutely could introduce complexity. There's definitely a trade-off.
So why do it?
The trade-off WhatsApp makes is purely for raw speed, especially minimizing latency for delivering that first message when you open the app.
Ah, okay. Minimize those round trips.
Exactly. Keep the logic close. Avoid network hops back and forth to distant backends. They mitigate the complexity risks through that extreme isolation we talked about, those independent Erlang processes, plus really rigorous testing.
So the performance gain is worth the management overhead.
Apparently so. They found it pays off, especially when you're dealing with billions of connections where every millisecond really, really counts.
That makes sense. And speaking of efficiency, you said a single chat server can manage, what, upwards of 1 million concurrent connections? How on earth do they pull that off without just melting down?
Yeah, it's impressive. It really comes down to avoiding unnecessary work wherever possible.
Like what?
Well, things like those typing indicators,
Sure.
or presence updates showing someone's online. They get batched up and rate limited.
So they don't spam the system.
Right. Message acknowledgements, the check marks, use really lightweight protocol messages, not big data transfers. And they're constantly monitoring idle sessions and basically kicking them out if they're inactive for too long.
Calling the herd.
Pretty much. They relentlessly optimize for that critical path, just delivering the message. Everything else is treated as secondary, less critical.
Okay, so when I actually send a chat message, my session process coordinates through backend chat nodes. How does that work?
Yeah, they route messages peer-to-peer within this back-end mesh of nodes. And remember, for every single message you send, there might be multiple related updates flying around too.
Like delivery receipts, typing notifications, profile picture updates.
Exactly. And crucially, many of these related updates have reduced delivery guarantees.
Reduced guarantees, what does that mean? Like, they might not arrive.
Not necessarily that they won't arrive, but more that they don't need to arrive perfectly or instantly. Think about it. Knowing someone is typing maybe a second late, is that a disaster?
No, probably not.
Right. So by consciously relaxing the delivery guarantees on these non-critical updates, they keep the system focus laser sharp on core message delivery. It significantly reduces the overall load and, honestly, simplifies the backend logic quite a bit.
That's actually really smart. Pragmatic.
It's very pragmatic, yeah.
Okay, let's shift to the back-end systems themselves. You often see back-end systems at scale kind of sprawl and become these huge monoliths, right?
Oh, yeah. That's a common pattern. Or maybe trap.
But WhatsApp seemed to have a really strong operational reason to resist that. Survival, basically. You said their back-end is split into over 40 distinct clusters.
Yeah, over 40. Each handling a really narrow slice of the product. You've got clusters just for message queues, others just for authentication, spam filtering, multimedia handling, and so on.
That sounds like microservices almost.
It's very much like that philosophy. This kind of logical decoupling is incredibly powerful at their scale.
Why? What are the benefits?
Well, first, it limits the blast radius of failures. If the spam filter cluster has a problem, your message delivery isn't affected.
Okay, containment.
Right. It also speeds up iteration for different teams because they're working on smaller, independent services. And you can optimize the hardware very specifically for each function. Spam filtering needs different resources than, say, multimedia storage.
Makes sense. So it was kind of microservices before it was the big buzzword.
Yeah.
Driven by sheer necessity.
You could definitely say that.
And you mentioned redundancy is built in through Erlang. Clustering nodes within a cluster are meshed, they self-heal. But they take it even further with this idea of islands of stability.
Yes, the islands, this is another layer, they group back-end nodes into these small, redundant clusters they call islands.
Okay.
Each island is responsible for just a subset of the data. Typically, you'll have 2 or more nodes in an island, a primary and a secondary.
Active, passive?
Exactly. If the primary node goes down, the secondary takes over instantly. And importantly, each island is also isolated from the other islands.
So what's the real magic behind this island concept? Why not just replicate everything everywhere?
The magic is that it adds this really powerful layer of fault tolerance without the massive cost and complexity of full replication across the entire system.
Ah, okay. Cheaper and simpler.
And faster recovery. Most failures will only affect one single island, so the recovery process is tightly scoped and incredibly quick. It's like having, lots of small, self-sufficient life rafts instead of one giant Titanic that sinks if it takes one bad hit.
That's a great analogy. Okay, so islands handle the back-end resilience. Now, when messages need to move at sub-second latency, you said traditional database thinking kind of goes out the window.
It pretty much has to. WhatsApp's architecture leans hard into raw speed, concurrency, and even accepts a degree of, volatility you wouldn't normally see.
Volatility. How so?
Well, when you're processing billions of messages, every millisecond counts, right? Their whole approach to data is fundamentally different from your standard relational database model.
So how do they handle data? What are the key features for this extreme speed? You mentioned ETS tables earlier.
Yeah, ETS is huge for them. So first, data access almost universally follows a simple key value pattern.
Like looking up a word in a dictionary.
Exactly. Quick lookups. And whenever possible, that data lives right in memory, using Erlang's ETS tables.
ETS, Erlang Term Storage.
That's the one. Think of it as a super fast in-memory database that's built directly into the Erlang runtime itself.
So no network hop to a separate database server.
Precisely. That lets them retrieve data with incredible speed. And most of the database logic isn't in a separate database layer. It's embedded directly within their Erlang application code. Fewer moving parts, less latency. Crucial.
Okay, in-memory is fast. I get that. But what about persistence? Messages eventually need to be saved reliably, right?
Right.
And what about those DB frags you mentioned?
Good questions. For persistence, the actual writes to disk happen asynchronously.
Meaning?
Meaning they happen outside the critical path of just getting the message delivered quickly. It doesn't slow down the immediate delivery.
Okay, and offline messages.
Right. For messages waiting for someone to come online, they use a smart offline cache. It uses a write-back model.
Right back.
Messages are written to memory first. They only get flushed to persistent disk storage if they linger in memory for too long or for certain critical durability needs.
Ah, so it acts like a buffer.
A critical buffer, especially during high-load events. In practice, they found something like over 98% of messages are actually delivered straight from memory before they ever even need to touch the persistent disk storage.
Wow, 98% served from memory. That's
It
amazing.
really is. As for DB Frags, think of taking a giant database table and smashing it into hundreds, maybe thousands of tiny independent mini tables. Fragments.
Okay, sharding, basically.
Exactly, sharding. But each data fragment, each frag, is owned by a single primary node. That node handles all the reads and writes for that specific chunk of data.
Only one writer.
Only one writer. It pushes updates to a passive secondary for redundancy. But this ownership model avoids one of the absolute nastiest problems in distributed systems, trying to manage concurrent access to shared state.
Right, avoiding conflicts.
Avoiding conflicts. And they hash these fragments, usually by user ID or maybe a session key, distributing them across many different processes and nodes.
So that don't write what will be read soon idea, using memory first. That seems like the genius move here.
It's a powerful example, yeah. Optimize for the common case, the 98%.
Instead of hitting slow disk immediately, bet on fast memory and reliable recovery. It completely flips traditional database design, but for messaging at this scale, it's a massive performance multiplier.
Absolutely, provided you have extremely reliable systems managing that memory, which Erlang helps provide.
And that sharding with dbFrag is what's the fundamental why behind breaking it up so much?
It comes down to reducing contention, spreading the load. It improves data locality, keeping data close to where it's processed, and it lets the system scale horizontally almost indefinitely without needing complex reshuffling of state every time you add capacity. It's fundamental to how they avoid complexity and bottlenecks.
So you don't have all the traffic trying to shove through one narrow gate.
Exactly. You've got thousands of gates, each handling its own little piece of the puzzle.
Okay, so putting it all together, well, what does this mean when, the rubber meets the road? WhatsApp's backend scaled? Sure, partly because of the clever initial design.
The foundation was strong.
But also because the teams learned where things actually crapped under real-world pressure, right? And fixed them before they exploded. They must have learned some hard lessons along the way.
Oh, absolutely. Scaling isn't just design, it's learning from failures and near misses. Constant refinement.
I heard one surprising anecdote. When hashes collided. Something about ETS tables.
Yeah, that's a classic. So ETS tables rely on hash-based indexing for that super fast key value lookup.
Right.
But a really subtle bug emerged where two different layers of their system were using the same hash function, but for different things, with slightly different inputs, maybe.
Uh-oh. What happened?
What happened was thousands and thousands of different keys ended up hashing to the same bucket or slot in the table, like everyone trying to cram through the same doorway at rush hour.
Performance tanks.
Performance completely tanked in that subsystem. But the fix was tiny, like a 2-line patch just to change the seed value used by one of the hash functions.
Just 2 lines.
Yep. And instantly, throughput in that specific subsystem improved by something like 4x, 4 times faster from a 2-line change.
Wow. But that highlights how deeply you need to understand the nuts and bolts, doesn't it? Even down to the hashing algorithm.
Absolutely. You can't just slap a Band-Aid on. You have to find that subtle root cause. It requires deep system knowledge.
Okay, another lesson came from something called selective receive. You said Erlang has this feature. It's useful for control flow.
Yeah, it lets a process wait for a specific type of message in its mailbox, ignoring others for a while. Useful sometimes.
But it became a bottleneck. How?
Under really high load, if a process's mailbox got stuffed with tons of messages, it could get stuck spending too much time just scanning through that huge queue, looking for the one specific message it was waiting for. Everything else gets delayed.
So the waiting itself became the problem.
Exactly. So the engineers had to get creative and work around a feature that was actually supposed to be helpful.
What did they do?
Things like draining the whole queue into temporary storage first, then processing it. Or splitting the logic across multiple worker processes so no single process had too big a mailbox to scan. And just consciously avoiding selective receive in really performance-critical code paths.
So even well-designed language features can bite you at extreme scale.
Definitely. It proves that every tool has its limits when you push it to the absolute edge. You have to know when not to use a feature.
And finally, a really big lesson. cascading failures aren't always load-related. One of their worst outages didn't start with a huge traffic spike or CPU melting down.
No, not at all. It was much sneakier.
What triggered that perfect storm then?
It started with a network router silently dropping traffic for a specific VLAN.
A VLAN, virtual local area network.
Right. Basically a way to logically segment the network, the seemingly minor network hiccup, invisible at first.
Yeah.
It suddenly caused a massive storm of disconnects and immediate reconnect attempts right across the cluster. Nodes couldn't talk to each other properly.
Oh, wow. Reconnection storm.
Exactly. Which then led to overloaded message queues between the remaining nodes, some nodes getting stuck, the cluster state becoming unstable. Internal message queues went from basically 0 to 4 million messages backed up in seconds.
4 million. Just like that.
Just like that. The only way out was a hard reset of the affected systems.
Yikes. So what's the takeaway there?
It really demonstrates that even with a solid design for failure philosophy like let it crash, these external unpredictable events will happen. Network gear fails silently. Things you don't control break.
You can't predict everything.
You can't. The key then becomes how quickly you can diagnose what's happening, contain the damage, and recover, and how resilient your overall design is to these unexpected external shocks. That island architecture probably helped contain it somewhat.
Right. So looking back at everything we've discussed, what we've really seen is an architecture that's, I guess, elegant in the trenches.
That's a good way to put it.
It seems built to handle chaos without actually becoming chaotic itself, to scale without needing heavy centralization, and to fail gracefully, without taking all the users down with it.
Component failure, not system failure.
So, for you listening, what stands out most to you about their approach? Is it that let it crash idea?
Or maybe the islands of stability.
Or that really radical in-memory database design? It definitely reshapes how you might think about robust system design, doesn't it?
It does. I think this deep dive into WhatsApp's backend really shows that sometimes the most sophisticated solutions aren't born from layers of complex cleverness, but from radical simplicity and a deeply pragmatic understanding of operational reality at massive scale.
Pragmatic is the word.
It's a design that's meant to withstand sudden spikes, silent regressions, global outages, because it fundamentally expects them to happen. It's not about preventing all failures, but about enabling quick, contained, and almost elegant recovery.
So here's a final thought for you to mull over as you go about your day. Think about this. How might WhatsApp's core principles that focus on simplicity, on isolation, and on designing for inevitable failure, how might those apply to systems beyond technology?
Interesting question.
What other areas in life, or maybe in business, or even just in how we approach personal challenges? Where else could we benefit from that kind of let it crash, contain it, then recover mindset? Something to think about.